Now we're going to focus on half-life. So half-life is the time it takes for half of a radioactive sample to decay. So if I started with 100 grams of uranium, how long does it take for that 100 grams to become 50 grams of uranium, where the rest just decayed away? I wrote way too big for that, but it's all right, not going to be too important. What is going to be important is that half-life is a part of a bigger topic, and that bigger topic is radioactive decay. So it's the decay of radioactive nuclei. And so for the exam, it's going to be important that you can do two things with this topic. One, some basic calculations using a few formulas I'll give you, and two, understand conceptually how half-life can be calculated. And so potentially for some of these problems, you won't even need a calculator. So there are two main equations that you need to know for half-life and exponential decay. The first one is N equals N naught times E to the power of negative lambda T. So, a lot of variables here. N is just the final amount of radioactive nuclei. I'm gonna say that a lot and write it a lot, so I'm just gonna write it as rad nuke. And naught was my initial amount of radioactive nuclei. The other two variables that are raised to the power, lambda and T, are usually the most confused. So lambda is the decay constant. So the decay constant is just going to be the fraction of my radioactive nuclei that decay over some amount of time. And that some amount of time could be a second, a year, a day, a month. I don't know. The only way that you're going to know is based on what time they give you. So for time t, that is just going to be how long you allow the sample to decay. So let's say I tell you that, hey, this sample decays for 500 years. I'm going to tell you the decay constant in years. So if my decay constant is the fraction of nuclei that decay per unit time, I'm going to tell you what fraction of the population of nuclei decay per year. So an example of that would just be if I had, let's say, 50 radioactive nuclei, and then 1 year later, I find out that I have 40 left. Well, that means of my original sample, that 10 had decayed. So 10 over 50 is just 0.2. My decay constant per year would be 0.2. 0.2 of my overall sample decays per year. So what happens the second year? Well, in the second year, I'm going to take my 40 radioactive nuclei. That's how much I had. I'm going to apply the decay constant to it. And I just established that the decay constant is 0.2. So that means that of my 40, 0.2 of 40 is 8. 8 of those 40 are now going to decay. So I'll have 32 radioactive nuclei left. So the number of nuclei that decay per year changes. As my population gets smaller, the fraction that actually decay will also get smaller. Now, what doesn't change is the decay constant. That decay constant is a constant. It's going to be constant throughout the entire decay process. Now, it's nice that I'm using 50 particles and that the decay time is a year, but that isn't always going to be the case. Now, what I want to do is, now that we've kind of talked about the n equals n naught e to the power of negative lambda t, there's one other thing you need to know, and that thing is the half-life. If I actually took this sample and I kept decaying it down, so I then took another year, I would say, oh, well, 0.2 of that is going to decay, which is roughly 6.4. So 6.4 of this would be like 25.6. And I could do another decay. I'm not going to hit with a whole number my actual time it takes for my half-life to occur. I'm not going to have a solid integer for a year when I have 25 of my radioactive nuclei left. Now, what's nice is there is a formula using the decay constant that you can use to find the half-life. And that formula is just T 1/2 the time it takes for half of my original sample to decay, my half-life, is equal to the natural log of 2 over my decay constant. So if my decay constant is higher, more of my actual sample decays per unit time. That means that my value in my denominator is larger. And if that value is larger, my half-life will be shorter. They're inversely proportional. Makes a lot of sense. The more that decay, the shorter it'll take for me to have half of my original sample. That is basically all you need to know for radioactive decay. Now, that is definitely a summed up version. You can go a lot more in depth. Believe me, I spent the past 2 hours trying to give a very in-depth analysis before I realized I would be wasting your time if I went really in depth here. So this is the summary. You can totally see what I mean if you look at the time of this video and the video before it. So now that we've talked a little bit about it, I'm sure if you haven't reviewed this in a while, it's still a little bit shaky. So let's just do a few practice problems that you would potentially see, and we'll kind of call it a day in a way. So the decay constant for a radioactive substance is 3.85 times 10 to the negative 4 per second. How long would it take for there to be 50% of the original amount of radioactive nuclei? Now that 3.84 times 10 to the negative 4 would automatically kind of scare me if I was looking at this for the first time. But what that means is if I take that number and I just write it out, this is the fraction of nuclei that decay per second. So if I actually wanted to write this as a fraction, I would just take the inverse. You don't need to know this. And so this means that if I have 2,598 nuclei, 1 decays per second, or that's the proposed probability. The odds are one of those is going to, one of the nuclei is going to decay per second. So how long will it take for there to be 50%? Well, my two formulas that I know is this one and T1/2 is equal to ln of 2 over my, lambda, or my decay constant. ln of 2 is a set number, just 0.693, so no matter what, I know what that is. And I know what my K constant is, or my decay constant. Sorry, there's a reason I keep mixing those up, and I'll tell you at the end. So I don't even need this formula at all, because all I'm looking for is how long would it take for there to be 50% of the original amount of radioactive nuclei. That is just the half-life. They're just not saying it's the half-life. So I am trying to find the half-life, and my half-life is just going to be ln of 2 over the decay constant, and I know that. So my decay constant is equal to ln of 2 over 3.85 times 10 to the negative 4. I just prefer writing it like that. And that would be 1800. And 1800 what? My decay constant is in seconds. So this is 1800 seconds. It'll be 1800 seconds, or in other words, 30 minutes, for my sample to be reduced to half of its original size, I guess. I could have done this another way, and the other way would have been, funnily enough, using this formula, where I would have just said, well, let's say my original n value was, that's not my original, let's say my original n value was 100, and half of that would be 50. Well, if I divide that out, I would have 0.5 is equal to e to the power of negative lambda t. Only issue is I don't know my time, so I'd probably be a little bit stumped there. I'd have to find an alternative method, but straightforward, half-life equals ln of 2 over my decay constant. So carbon-14 has a half-life of 5,730 years. Takes that amount of time for half of a sample to disappear, to decay. I just say disappear because we don't really think about it after it decays. After 11,460 years, how much of a 200 milligram sample will remain? Well, the first thing I would do in this case, because all I have is half-life, not going to write the word out, whoops. Redo? Yeah. I would just write out what variables I have. T 1/2. I have my total T. And then I have my initial amount. Great. Now, this is one of those conceptual questions you don't need a calculator for. And even if I tried to use a calculator, it would probably take me at least a little while. But I am given the half-life, how long it takes for half of the sample to decay. And that number, or that amount of years, is how much it's going to take for each amount to decay. What do I mean? Well, if I have, this is going to be a funny example. Let's say I have this amount of a substance. Great example. After one half-life, in this case, 5,730 years, I'm going to take that original sample, and basically, I'm just going to have half of it. Makes a lot of sense. Let's say that's half. So, what happens after the next half-life? Well, I'll just take that same amount that's remaining, and I'll cut that in half. So, what am I trying to say? I guess in simple terms, without getting all excited about this, look at your time and see if that is just a multiplet of your half-life. I'm given 11,460 years, and I know my half-life is 5,730 years. 11,460 is 2 times 5,730. So what does that mean? It means I can have 2 half-lives in that time. Whatever my initial amount was, in this case 200, after my first half-life, this is my half-life, I'll have 100. And after my second half-life, the years 5,731 to 11,460, I will have half of that. So after 11,460 years, 50 milligrams of carbon-14 would remain. We're just going to keep on getting hit with these. It's all right. We have a half-life of 232. What fraction will remain after 696 years? Well, 696 is just 3 times 232. So what fraction will remain? Let's say I have 100% originally. Let's actually just make a quick table, I guess. So I can just predict that I'm going to run out of space. Fraction, and then time, and then say the half-life. What half-life are we on? All right. Yeah, that'll work. So I have 100% of my original sample when time is equal to 0, and I have not had a half-life yet, or I've not gone through a half-life. Now, what's going to happen? How much am I going to have after 232 years? Well, I'll have 50%. That's the half-life. And that means we'll be through our first half-life now. Going even further, after 464 years, we're now down to 25% of my original sample. That is my second half-life. Now, after my third half-life, 696 years, we will be down to 12.5%. And that is 3 half-lives. So the answer, 12.5%. Lastly, given the following graph, what is the half-life in days of the given substance? Great. Time, massive substance. Well, what is my initial mass? Here I have at time equals 0 days, 16 grams. So time, 0, grams, 16. Well, now what? I'm going to try to find a place on this graph that I have some kind of intercept or some kind of value that I can identify as a integer for time and an integer for massive substance. So what do I mean? Well, I originally have 16 grams. I know at my half-life I'm going to have 8 grams, and at the half-life after that I'll have 4 grams. So at 8 grams, how much do I actually have of this substance? Well, sorry. At 8 grams, how much time has passed? Well, I am exactly in the middle. And I could assume that this is 1 day, although assuming is never really that good. What I could do instead is I could just go and say, oh, well, look here. I have 4 grams at 2 days, but that's not my half-life because 4 grams isn't half of 16 grams. But I know that 4 grams that occurs at 2 days is the second half-life. So at the second half-life, I'm at 2 days, which means that what's my first half-life? It's going to be half the time before my initial and my second half-life, which means 1 day. and at that point I would have 8 grams. So given the following graph, what is the half-life in days for the given substance? The half-life is 1 day.